Good afternoon, students. We have the Dr. Phumchai, our faculty here as well. So let me start by introducing the Dr. Supasorn Suwajanakorn. So officially, I say good afternoon to all. Welcome to the kind of reflection. Welcome to the SCAI seminar lectures. Today we welcome our guest lecturer, Dr. Supasorn Suwajanakorn, faculty of VISTEC, Rayong. Dr. Supasorn is one of the authorities in AI on image synthesis. He was famous for his TED Talk 3 years ago on the fake video of real people, featuring the real Barack Obama with faked voice and message. Let me give you his brief background. Before settling down in Rayong, Dr. Supasorn was a research resident at Google Brain, working on geometric understanding in deep learning and image synthesis. He finished his PhD from University of Washington, working in graphic vision group called GRAIL. And his goal is to bring computer vision out of the lab into the real world, make it really work in the wild. He went to Cornell for undergraduate program, working on social graphic algorithm, and later on get inspired with the computer visions. So welcome Dr. Supasorn. The talk he is going to give us today is titled, Can AI Really See Now? So the floor is yours, Dr. Supasorn.
Hello. Can you hear me clearly? Okay, thank you so much, Kabajan Babasak. So thank you for very kind words. So my name is Supasorn Suwajanakorn. I'm a lecturer here in VISTEC in Rayong, and it's really an honor for me to be speaking here in the seminar. So in this talk, I will share with you guys what has been exciting me for the past months and the latest of the latest research, like state-of-the-art research in computer vision. So this talk is titled, Can AI Really See Now? And so to answer this question, let's look at one of the, the most recent one. Let me see. Okay, I hope you see the, okay, I got stuck. My PowerPoint got stuck. Okay. So just a few months ago, a new research paper called Chris tried to solve the following problem. So given this input photo, right, and a text. So the text here said a zebra ahead of another zebra. So what this program does is that it can actually specify that particular zebra given the text alone. So it's not just any zebra, but the input text, the input that a user program to the type into the program is a zebra ahead of another zebra. And the program can actually specify which of the two zebras the users actually wants. And so this is unlike anything we've seen before, because it takes simply text and you can pretty much type anything to find the right thing you want to find in the image. Unlike previously, you have to specify and you can choose maybe just only one type of animal. You cannot just type text. But this came out December just last year, 4 or 5 months ago, and you can do this. So this research is actually possible due to another important breakthrough called CLIP. So CLIP is released by OpenAI, a big name, big company, I mean AI few. So CLIP is essentially a model that is trained on both text input and the image. So basically, someone gather a large collection of image and label like this one. If you have a photo of a cat on the left, it will say the label will say this cat has the most stunning, beautiful eye. It's just normal text that you can gather on the internet, off the internet. They have about 400 million of these pairs. So by training a really, really large model on this really, really large data set, you can do things like this. Given an input image, the user can type anything. In this case, a blonde hair, blue eye, young boy in a blue jacket, and the program will segment that particular boy for you. So the question now is, how good is it really, right? I think a lot of people might have seen a headline like this where AI beats human doctors in medical diagnosis. So in this case here, a team of 15 doctors from the best hospitals in China is competing against an AI company called BioMind on a brain tumor diagnosis. So the doctors actually took about 30 minutes and they achieved an accuracy about 66%, whereas AI took half the time and achieved better score, better accuracy. So, and when people say this, they try to defend themselves a little bit, and say that AI can't really do creative work. And so one of the things that I really like, there's another work. This one it also made the headline. So this is a painting, but it's not done by a human. It's actually done by a model called Generative Adversarial Network. It looks kind of crappy and like an abstract art, but turns out what's interesting there is that usually you will have like a signature of the artist, but not this one. This one has the actual equation for generating that painting. And so this is a generation for the Generative Adversarial Network that is used to generate this painting. And what I like about this is that this is the very first AI that got sold for a ridiculously high price. This is got auctioned for like 13 million baht. But so it's kind of look crappy right now, but I'll show you most recent ones and how far we have come as a few. You'll see the latest one this month soon, later in the slide. And so to actually evaluate this objectively, right, to compare AI versus human, we have to have a benchmark, a better metric first. And so researchers look into this problem called image classification. The problem setup is the following: you have an image, and just tell me what animal this is. This would be the correct answer would be lion. And so we try to compare, how humans perform on this task versus AI. And so we can measure the error rate, or how many images you got wrong. And the baseline for human is at 5.1 is the human error for this kind of task, for image classification task. And in 2010, so again, this is error. So the lower, the better. In 2010, the best AI model got an error about 28%, 28.2%. 2011, 25.8%. 2012, though, so before 2012, all the progress has been really slow and stagnant. But all of a sudden, in 2012, a work called AlexNet was able to improve the error accuracy by a huge jump compared to other previous work. So what happens in year 2012? So what happens is that people use this thing called deep neural network. It sounds very new, but turns out it's very old. This one is invented in almost 1950, which is almost 50, 60 years ago. The concept is actually very simple. So in this case, if you want to classify whether an image is a dog or a cat, you feed that image into the left side, the input side, right? So this node could represent all the pixels. And the whole idea is that, to compute the value, of this yellow circle, you're just going to compute the, weighted sum of the number from the previous layers on the red. You're going to sum all those numbers together like that. And if that sum is above some number, some threshold, you're going to fire that number out to the next layer. And even the most complex AI still relies on this very simple concept. It's just very simple, and it's partly inspired by the human brain, all the neurons, all the dendrite. The core concept turns out to be very simple, very, very simple. Just sum the number together. If it's above some number, just fire it out, send it out to the next layer. So the right side would be 0 or 1. 1 could mean this picture is a dog. 0 could mean this is a cat. And that's very simple concept. It's not the only one that makes that breakthrough. The other important component is in year 2009, we actually gathered this huge data set called ImageNet. So back then it's really huge. It contains about 15 million images, and it has about 20K categories. So inside that is just regular photos you can find off the internet, a dog, a pizza, and anything. But once you combine this large, really large data set with 50-year-old model, breakthrough happens. So in 2013, it got much better. And 2015 is the first year that an AI system actually beat human on this image classification task. Another task we can look into when we compare the human versus AI is image captioning. So given this image, the goal is can you write a description for this image? So in this case, we would expect a zebra standing next to a zebra in a dirt field, for example. This one would be the expected caption could be a man sitting on a couch using a laptop computer. So it turns out these labels are actually generated from an AI system. And so you might say, oh, this works pretty well. This seems to be like understanding what's happening in the image. But there are some corner cases here. For example, this image, it turns out, the program said this is a cat sitting on a toilet in the bathroom. This is no cat, no toilet at all. So this one, I think it's a white cow standing on a top of a field. And turns out there's no field. This is like flying cow. And so the first time researchers, see this, they're sort of confused a little bit. What's happening? And so in the field, there's a term called overfitting. And this could be because, in the data set, we never have cows anywhere beside, green grasses, right? Green grass. And so whenever, an AI sees, say, like a patch of white and black, it may automatically assume that it's cow on, some field, like green field. But it might not really understand, what does it mean to be standing on or grass or sky. So that's that has been like the main question that researchers try to answer. Like, does it really understand? Because we see it does amazing things before, right? But is it because the tests that we have for those AI is just too easy? Does it actually understand anything? Or in this case, it's really far off, right? And like even a kid would not make this kind of mistake. And so to put this to the test, right? Researchers came up with a harder data set called ObjectNet. So in this case, they put, ordinary objects in weird places. For example, if you have a hammer, it usually be in like a wooden shop, but this time they put like a hammer on a bed, and instead of like an upright chair, it's just a fall down chair in a bathroom. So can AI systems solve this problem? And so, so this is the results if we actually test an AI system on this kind of data set. So this is a flip a little bit. I'm showing here an accuracy score. So this is higher the better. It's inverse of error. So this one higher, the higher the better. And so the green line is the AI model on the old data set called ImageNet. So achieved right now in 2019, 96.2%, which is pretty good, right? And human accuracy is only 94.9%. And so when we actually test the same system on this harder data set called ImageNet, where objects are in weird places, the accuracy drops a lot to 55.1%, whereas the humans would stay the same at 94.9%. So what's happening here? And so one of the most eye-opening work in this area is called adversarial attack. So what's happening here is that if you have an image, a temple, right? And if you feed this image into an AI system, it will answer correctly that this is a temple. The sky only changed just by a tiny bit, but to human eyes, they look the same. They're temple. But what happens is that AI thinks that this is, a bird instead of a temple by just adding noise to the input image. And so it turns out you can do the same for every kind of image, not just, a temple. you can turn the school bus or a dog or the soap dispenser into an ostrich by adding some kind of noise, by manipulating tiny bit of the pixel of those images. And so this is called adversarial attack. And there's a lot of work on this kind of field, like, can we actually trick AI? Like, so this is related to the question, because if AI really understand the scene, it would not make this kind of stupid mistakes where, even 5-year-old would not make. So in this case, so what the researchers did was that they try to trick a system that can currently correctly classify the image as banana. And they try to trick it into thinking that it's a toaster by, having this thing, like a printout of a toaster and then put it there, but it doesn't work. Okay, AI is good enough to know that that's still a banana. But turns out they can print a special pattern, looks like this, and totally fool this classifier into thinking, okay, this is 99% toaster by having this weird pattern. And this also happens in real world. And this is a real, someone tried to tape the stop sign and try to turn this into something else. And this works in the real world, like with an actual, robot or a car with a camera and see the real sign. And the car actually interpret this sign as a speed limit. So instead of stopping, it could just keep driving with 45 miles per hour. And Tesla cars actually, some people in China actually trick a Tesla car with a tiny white sticker too. But this is quite a while ago, so I presume this is already fixed. So what happened is that they put this white sticker on the ground, and Tesla car just think it has to turn away, and I don't know what happened there, but just that small sticker, white sticker, can already trick your Tesla car. And this is quite scary also in medical field, right? Because in this work shows that you can just simply rotate the input photo by certain calculated amount to trick it to change the diagnosis from benign to malignant or cancer. Not only that, there's a lot of face recognition system built in, especially in China, where you have millions and millions of CCTV, and they actually run facial recognition software, right? So this research also tried to fool the AI system by design a specially coded glasses where someone can wear and change the identity from the top row to the bottom row. So for example, the guy on the top left is, once he wears the glasses, he becomes woman in the bottom row. That's what the AI would recognize as, change. You can actually totally change the identity of a person by wearing that glasses. And so before I move on, I'd like to give a very quick introduction about computer vision. So this field that I'm working on is called computer vision. So it's part of AI. And the goal of computer vision is to basically teach computers to see and understand things just like humans do. It's part of artificial intelligence field, where we try to replicate, human intelligence in a machine. And it also overlap with a field called machine learning, where the goal is to teach, machines to do things without writing rules manually. How can we teach machines to learn from data? So a few of the problems in computer vision includes image recognition segmentation. For example, given an image, we want to specify, can you classify every single pixel into different semantic things like building, door, sky, vegetation. Another important problem is image captioning. Given an input photo, can you actually write a description for that photo? Another is 3D understanding. Given a regular photo of a bird, humans can we can sort of tell the rough shape of this bird. We can sort of infer that, okay, the ground floor should be a plane. Can we actually teach the same thing, the same 3D understanding? How can we teach computer to understand the same shape as humans do, even though we only see one, see this bird from one angle from one photo? So one of the most, so this is one of my favorite work. It's done by my advisor in undergrad. So he looked into, so back then we don't have Facebook or Instagram. We have this Flickr. So it's a website that people post a lot of photos, random photos, tourist photos. And what this project does is that, what if we gather a lot of photos of, the Statue of Liberty? Can we actually reconstruct that Statue of Liberty in 3D? And turns out you can, by just collecting different photos of different tourists from different time, from different angle, from these are just tourist photos, but the project is able to convert all this unstructured, unconstrained 2D photos into some sort of 3D model. In this case, it's called point cloud because it's just points, 3D points. And this is done it's a little bit old, in 2006. And so 3 years later, from the same lab, they actually gather photos of the entire city, and then try to apply the same algorithm to reconstruct the whole city. And so they named this paper "Building Rome in a Day" because they can actually build 3D model of the city in one day, as opposed to so this is a famous saying that Rome cannot be built in a day or something. Rome is not built in a day, but they can pull this off and build the entire thing in one day. But ironically, I don't think this is Rome. I think this is Venice, not Rome. And so, as you can see, these are just point clouds, right? It's very sparse. So a year later, people try to make it like a really, really dense 3D model. So again, we can reconstruct, the inside of this cathedral in 3D without, someone actually walk inside with laser scanner or anything. We just gather, tourist photos of this place, and we're able to convert this into a 3D model of the inside. And so this is quite old, 2010. And here's the latest one, 2021, right? It's pretty much the same idea, but with, all the modern machinery with deep learning. Yes, and this is the current state of the art. It's solved exactly the same problem. Given unstructured photos from the internet, from anyone, from tourists, can you actually build a 3D model of any particular place? And so when I was in a PhD, I was also inspired by this kind of work. But what if instead of photos of landmarks, what if it's photos of someone, faces? We have Facebook, we have a lot of photos of a person. Can you actually reconstruct a 3D face model of someone by analyzing a lot of photos of that person? And turns out we can. So in this case, we just search when we want to construct, say, a Daniel Craig or Hillary Clinton. We just search on Google, gather a bunch of 100 images of them, and we're able to construct a 3D drivable model. So on the right are reconstruct models of 9 people, and we actually drive all those 3D models with a driving sequence of George Bush on the left. So the input driving sequence is just a George Bush video we gather from off a YouTube video, and we're able to drive all this 3D face model that were constructed from internet photos of them. And so these are nice and things. So humans also have this ability to imagine things, right? We not only see things and understand, we're able to imagine things too. So the question is, can AI also imagine? Can AI also dream up things? So in this field is related to also image synthesis. How can we synthesize things? How can we synthesize data or images? And so one of the breakthroughs is called GANs, or Generative Adversarial Networks. And it's a kind of, a model that can generate things as long as you throw some examples to it. In this case, you can gather a lot of face photos, have the model look at, 10,000 of face images. And once it's done training, it can actually generate new kind of faces. So what you see, all these faces are not real. They're all computer generated face images. And to me, I can't tell apart which is real. Like if you put two images together, I can't really tell apart which one is real. So that's the current state of how good AI can do image synthesis. So image inpainting is also another problem. So suppose you have this image, but part of the image is missing. Like if you have, like some white out places, or you're missing some of the place in the input image. Turns out, an AI system can fill that part in pretty realistically. Like I can't see how it just blends seamlessly into the input photo. And so it has a lot of application in, image editing, where, if you want to remove things like a Photoshop, it can fill in automatically. If you hate your face, you can change your own eyes. You can change your own facial features. And this works by, AI actually seeing a lot of face photos before. So it sort of infer that this part should be eyes, and how, it learns how eyes look like and try to fill in the rest when you mask it out. And so, and one of the most shocking results that just released almost just 2 weeks ago, this is very new, like only in this month, is a model called DALL-E. So what this one can do is that, given the text down there, I'm not sure if it's too small, the text is a Shiba Inu wearing a beret and black turtleneck. And this system can actually generate realistic image according to that input text. And this is super realistic. And this is another example, like a teddy bear on a skateboard in Times Square. So these photos are not real. They're generated by an AI system. And not only that, so you can also input really, really long text, like teddy bears mixing sparkling chemicals as mad scientists as a 1960s Saturday morning cartoon. And this is what, it drew. And it can also, have different variations for that only one text. You can also, change different style. Instead of, as a cartoon, you can say as digital art, and, it can generate these amazing things. I can't even, draw properly. And this, to me, this is really amazing. And it understands a lot, right? Teddy bears, like scientists and mad scientists, also, you have to do crazy things with their experiments and ask, certain kind of size, in this case, a digital art. And so related to the introduction to, what if this is a different problem? What if an AI got an audio of someone? Can you actually generate video of that person speaking? And so we look into this problem, and the first thing we have to do is to find the sort of data, right? And luckily, Obama has this weekly address where he speaks for like 2-3 minutes every week. And so we gather all of them over the past 8 years of his presidency, and teach an AI to do this. So the input is just an Obama voice, and we're able to generate this 4 videos. So I'm not sure you can hear the audio, but you can see this result online. So he's actually speaking something, and these videos are all generated so that he speaks, that audio. I'm gonna go for, I think a little bit short on time. So there's some other kind of work too, and this is more like computer graphics. If you have an image of a waterfall, can you actually animate it? Can an AI system predict, the actual animation of that, waterfall image? Turns out it can. And I'm just gonna go quickly because I think we're a little bit short on time. And so there's also another creative application. For example, you can turn a sketch, a designer sketch, into a realistic, in this case, realistic bag. Or you can turn just a sketch or scribble of human faces into realistic photos. So it seems like AI can do a lot of things, right? But the question here is, so what are we doing? Like what researchers in this field are doing? What are the remaining challenges? So one is that to give an example, right? When I want to teach a child to recognize this animal. So this is marmot. It looks similar to a squirrel, but it's not. It's a marmot. like they live in the Pacific Northwest in the US. So to teach someone to recognize this animal, especially a kid, I can just give them just one photo of this marmot, and he or she will be able to recognize this almost instantly, right? Even I give them a different photo, from different angle, this marmot has a different pose now. He or she can still recognize this, right? And if I have two images, which one is marmot, which one is squirrel, the kid will still, probably answer this correctly. Whereas currently, when we train a machine learning algorithm or an AI system, we have to throw like thousands of images. Previously to teach a machine to understand what the lion, you have to have at least maybe 100,000 or 1,000 images of the lion in order to teach it to understand what how a lion looks. So how do we make AI be able to learn from very few images or just one images like human do? How do you make this learning process much more efficient? And this is the field called few-shot learning or zero-shot, one-shot learning. Like how do you learn from just one example or few-shot or few examples? And also, being able to solve this would have really big implication because, we have a lot of photos, like people capture photos. We have new photo, like billions and billions of photos every day. None of them has labels. So if you're able to learn from just images without labels, we will be able to leverage a lot of existing data that we would, otherwise have. If our system always has to use labels, then we cannot utilize all these, images in the internet. So I have maybe 20 minutes. So for the rest 20 minutes, I want to cover briefly the research that we do in our lab, Vision and Learning Laboratory. So we're interested in the few-shot learning problem. So this is one of the problems we picked to, as a starter. So the problem that we look at is called part segmentation, where given an image of Joe Biden, can you actually specify where his eyes are, where his nose and mouth? And on the right is just a visualization of the output, right? The eyes are yellow and green, hair is green. So this is the problem setup that we're looking to. So traditionally to solve this, right? Or one way to solve this problem is to gather a lot of paired data where you have input photos and you hire someone to actually create this label, create this segmentation labels. And once you have this really, really large pair training data, then you can train an AI algorithm. So our research shows that, or develop a new algorithm so that you can only acquire one label as opposed to 1,000 labels. And so this is our results. We can actually achieve this kind of segmentation by learning from only one label example as opposed to 10,000 labels. And as you can see, there's still room for improvement in terms of accuracy. But the main finding that we have is that we're able to achieve this kind of quality by using about 30 or 50 fewer training data or less data than other traditional techniques. Like in this case, we only use one, whereas traditional techniques would require hundreds or thousands segment labels. And so the idea is actually so I showed this work before. It's scans, right? It's generative model. So traditionally, this model was designed to generate things, to synthesize things, and that's it. That's the only thing that it can do. It can do nothing else, just generate nice things. But our research idea is to actually, the hypothesis was that, if you have an artist who can draw like face like this, that artist has to understand something about faces, has to understand some like the structure of the faces. Can we actually distill the knowledge from this artist and use it for something else? So the work is called repurpose GAN, or repurpose this model for a different kind of task. And in our paper, we use this generative model to solve semantic part segmentation, which is a different task. This is example of the result. So on the left is the part annotation. You can see this. This is the only label that we provide to the model, only one label. And the model is able to find where the wheels are on different, different cars with different models, different pose and different color too, and find all the glass, all the headlight by just training on one example. And we can do segmentation on videos as well. So these results are trained with 10 labels. Look, we only labels 10 horses, and it's able to generalize to multiple horses in the scene. It can find all the legs, all the head of all these horses simultaneously. And so another kind of work is called unsupervised, right? For example, so this work looked into the problem of key point detection. So key points are, if you have a plane, the key points of the plane could be, all the important parts of the plane. And, one could have shows, okay, the cockpit is an important one, the two wings are important one. And so key points have a lot of use in robotics or self-driving car. So when self-driving car wants to localize itself, right? One of the ways is to find all the key points of the scene and then track the key points. And sometimes when robot wants to grab things, the robot has to know the orientation of those objects first. And one of the ways is to detect all the key points of the objects and then use that to infer the orientation of the objects. So in this research paper, we want to find key point. That's the problem with this research paper. But usually, again, traditionally, to solve this problem, we have to gather a lot of data. We have to have a lot of airplanes, and then we have to hire someone to actually label where the key points are. But this work actually shows we can do this with 0 labels. We remove the humans from this process entirely. And this is work done when I was at Google in 2017. And so this is the results. So we asked the AI to please pick 10 important points for these planes. So the AI goes ahead and find important 10 points of this class instance of this class airplane, and also figure out automatically how to track them. So we never actually gather any data at all. We never have pair training data where humans actually label where those 10 key points should be. So back then we asked whether the AI is actually cheating by just putting points on a rigid structure and then rotate it with the plane. And so we tested with a weekly car to see whether the key points are actually tracking the right places. So in this case, the orange points is still tracking the wheel. It's not like on a rigid box, but it's actually tracking the right part. And we also have preliminary results on real world images of cars. So it can still track real world images of cars. So another problem in our lab is related to view synthesis or 3D reconstruction. So this is done by 3 students, and I think the middle guy is from EE Chulalongkorn. He was doing RA-ship with us for a year. So this paper is called Next Real-Time View Synthesis. So let me show you the results. We have a video demo. So what you see here is actually not video, as in it's not a video of someone swinging their phone in front of that food, but it's actually a render 3D model. And usually when you think about 3D model, right, it doesn't look real. It looks like 3D model, like a game 3D model. But this one is actually a 3D model that looks very realistic, as if it's a real video. So that's not really the key contribution of this work, though. So the first key result is that we're able to reconstruct this model in a very realistic manner, like as if it's a real video. It's really hard to tell apart which one is 3D model or which one is a real video. And second is that usually previously people cannot render such kind of model in real time, but we're able to speed up the entire process and be able to render this model in real time on a web browser, for example. So these are an actual demo on a Google Chrome, a web browser, Google Chrome, where you can actually see the 3D model of the capture scene, the food, and this scene with the very hard CD reflection, the rainbow reflection on the CD. So this problem is actually a classic one. It's called 3D reconstruction from 2D photo, or photogrammetry. And the setup is that you have a bunch of 2D photos of the object, and you turn that into a 3D model. And turns out there's an app on the iPhone where you can grab a bunch of photos of your object, turn that into a 3D model. And Google also uses the same technology to convert aerial photographies or satellite photographies into 3D model of the entire city. However, there's really challenging objects like glass jar or jewelry, or this plush toys with really thin hair. So turns out if you apply the traditional 3D techniques, like the one that Google uses for city reconstruction, you get results like on the left. And there's a lot of holes, a lot of things. And this is because, this water bottle is much harder than, like diffuse or matte objects, because, it reflects really complex light inside itself with reflection, refraction. And with the new technique that we developed, we can actually render this very realistically. And the idea is to have this, semi-transparent plane on top of each other and stack them to reproduce all the lighting in the scene. And we can also do this in all 3D, and we can still render them realistically. So this is like already a reconstruction of a 3D model. It's not 3D model rendered in a traditional way, but it's a reconstructed one. And one of the motivation here is that we want to convert, say, online products into, a 3D things where you can see it all around, right? As opposed to only see 5 images of the product you want from 5 different angles. You can actually wear a VR headset and actually hold that object in your hand. So if you're wearing the VR headset, you will actually see the model in 3D, and you can actually hold the model in your hand with the controller and look at all around in 3D. And we can also do the same thing, not just for objects, but also for scenes as well. And this is Yak Ti Tan Wat Phra Kaew, or other really complex light effects. And we also can do this virtual tour or Teo tip. If you want to go and Namaskar Pha Phutta Shinalath somewhere, you can gather the photos of that and then do the same kind of virtual experience. So we reconstruct the model also from tourist photos. So you can actually see the entire thing in actual scale, like really large in VR. And finally, the last work I want to show is called Diffusion Autoencoder. So a lot of people have heard of GANs and StyleGANs, and I have showed this. So it's a model that can generate realistic cling, very realistic photos. But in last year, there's a new model that people think that it might work even better than StyleGAN, and it can also do the same thing, generate a lot of realistic photos, but the working principle is very different from GAN. So this photo, we're interested in representation learning. And so in machine learning, right, there's a very big field called representation learning. And the goal is, suppose you have an input image. We actually want a compact representation of the input image. Like we want to turn that input image into something like only 5 values, or in this case, 512 dimension, where this vector encodes a lot of information about that image. In this case, the first dimension might capture whether this person is a male or female. The second one might capture whether the age of this person. The third one might capture the race of this person. So suppose we have this encoder, right, that can convert an input image into something compact and meaningful. We can actually do a lot. This is very useful because then we can do classification. We can classify whether this photo is a male or female by just reading off the number in this, vector or this compact representation. And so this is, one of the holy grail of representation learning. Can we actually learn? Can we actually build the encoder so that we can convert very complex like images where it contains millions of pixels into a very compact numbers, into a very compact vector like 500 dimension? And so our paper tried to build this encoder. And once we have this compact encoder, right, one interesting we can do is, what if we change, I'm sorry, I missed this part. So once we have this compact representation, we can actually decode it back to the original image and get the same girl back. But what if we change one of the value in this compact representation? Suppose we know which of the dimension corresponds to the age, and we add 1 to that dimension. Turns out this enables very interesting application, right? So we have this real image, and what we did is we encode that image into 500 numbers, change one of the numbers that corresponds to aging, and then decode it back. Then we can do age progression or regression with this very simple technique. And this is sort of an animation of that. So the goal isn't, this work isn't trying to solve age progression or regression. We try to find a compact representation. And that compact representation is useful for a lot of things, not just, age progression or regression. There is more examples here for age progression and regression. So I think it sort of knows that old people tend to wear glasses, so it also adds glasses to you. And it can also change other attributes as well, not just aging, right? There's a lot of attributes that are encoded in that 500 numbers. For example, you can even change, the appearance of your hair. In this case, make a straight hair curly. Or you can actually interpolate between 2 real images. And so these are, this field is called representation learning. It's also part of, it's a very important in AI. Oh, 3 more minutes. So the last work is sort of a fun one. And so our lab does computer vision, computer graphics, or the intersection of vision, graphics, and machine learning. So this is a collaboration work with Dr. Kostas Konstantinos. He's a researcher at Google Zurich. So what I show here is his previous work. So he took this football match video from YouTube and then turned that into a 3D model of that match. So his goal or his dream is to convert all this 3D match into 3D so that you can wear an AR goggle and then project the actual match onto a coffee table so that you can enjoy the football match from any angle, from any part of the stadium, or you can even zoom in once you wear the AR glasses. The problem, however, though, you can see all the players are reconstructed, but not the ball. Turns out the ball is actually harder than the player, because sometimes when you see, the trajectory, a straight line trajectory of the ball, it's unclear whether it's actually rolling on the ground or it's actually, airborne on the sky. It's inherently ambiguous. You can't really tell apart from the 2D input. And so we try to complete his dream by solving the ball part. And so we actually use AI, also deep learning, to figure out the 3D ball position from 2D monocular or single view video. So this is from also YouTube. We get this tennis match. Can we actually infer ball in 3D? And turns out, using a deep learning technique, we can actually infer the actual 3D coordinates of the tennis ball. And again, so the goal is to project this onto your AR glass, and then you can now enjoy the tennis match on your couch or on your bed. And I think that's all. Was running out of time. And here's our collaborators, interns, and I think a few are from Chulalongkorn actually, and also international collaborators, high school students who intern with us in summer interns. Thank you. If you have any questions, I think, okay, 7 minutes.
Thank you so much, Dr. Supasorn. I'm sure there would be many questions. We have about 5 minutes, 7 minutes. So maybe let's have the question from the Zoom first. Anybody would like to ask question? Dr. Pumchai, since you are here.
Oh, yep. I guess just a quick question. Have you put your work on paper with code so we can start playing with it?
Yeah. Some of them are we do have code, like the 3D reconstruction work. We released the actual source code and also get like collab work, collab project you can play around with. The latest one we're about to release, and yeah, the lead author is working on it.
Excellent. Other than that, I don't really have a question, but I really, I think this is very exciting. I guess my remark would be that I think we've come very much a long way. We used to say that this AI revolution or this emerging technology is kind of like made possible by the computational powers, but I kind of think that there's a lot more to it. I think I remember the days when the groundbreaking days, we were looking for biological brain to inspire how we construct the architecture, going back all the way to the cat brain, to neocognitron, and ultimately convolutional layers and whatnot. But I think what's happened post AlexNet world is that researchers have become very creative in their use of algorithm. And the example I like to use is GAN. Basically, GAN. I remember that GAN. Originally the intention of GAN was to improve learning, by creating fake. The creating fake was a side effect. It was a fun thing that came out, right? The real thing was to make the example more robust, the learning algorithm more robust to noise and so forth. So sort of like a generate fake example to see if the learning algorithm is robust to that added noise. And then it became something that takes a life of its own, this kind of fake video and whatnot. And I think, if you look at the modern AI communities, I can roughly sort of like see three kind of families, the visual people, the image, the vision people, the text people, and the graph theoretic. I personally, I certainly belong to the graph theoretic tribe. But I think what I admire most about the vision tribe is they like to play around, flipping from input to output, output to input, for say, take text, make the picture, from the picture to the text, from the composite to the element, take the element, make the composite. So they do a lot of interesting inversion. And so I guess linking to the topic of today, which is, can AI really see things? Do you think that, after, say, especially in the last 10 years of flipping this learning around, this paradigm from composite to element and to for embedding and all kind of stuff, has the visual AI community gone back to sort of like, say, all together, different modes of learning, simulation, fake example, and so on? Has it given more insight into whether or not we are capable of forming an internal model of reality? Because at some point we used to be settled on the fact that machine learning can just perform tasks, and we try to get to the general AI. But as you can see from adversarial attacks, at some point the reason we can perform adversarial attack with just a few flip in the pixel is because somehow there isn't a consistent internal model of what reality should be, right? But the visual AI community has done a lot of crisscrossing the learning path from real to fake to real and so forth. Have they been able to sort of like put together a more cohesive framework for understanding how an AI could conceptually develop an internal model of reality, so that they can't be thrown off by a few pixel flip, for example?
Yeah, so I can't say. I can only say for myself personally. Like I don't have the view of the entire field, and I'm pretty sure people have different school of thoughts. Even researchers have different, opinions on the same things. For me personally, I don't like, I don't see it as too special. I still think that, you know, even DALL-E, the one that can actually generate, you know, teddy bears, when you look at the limitation in the paper, for example, it does still stupid things. Like, it doesn't know the relative size of things and stuff like that. I think it still missed a lot of things, and it turns back to a lot of impressive things could be due to the fact that the test was too easy. You know, even image synthesis, for example, if I say, please generate teddy bear where half the body is something else, you know, humans can actually pretty easily do that. Or, you know, teddy bears in front of something, on top of something, where it's very simple to humans to solve. But once we have this more challenging test set, I would imagine, you know, all the magics could be gone. Like, you know, it's no longer impressive in that sense. And in some sense, if you do a really good job of regressing or doing pattern matching, pattern recognition, you can actually solve a lot of these tasks like pretty impressively without actually understanding anything at a higher level. You can do, you know, translation pretty easily. If you have seen like billions of text pair, you can do image generation pretty easily once you have billions of text, you know, these kind of pair data. So to me, I personally see it as, you know, we're still really far behind. You know, the gap is still pretty large, and a lot of things we see impressive, once you put it to the test with really, really challenging things, it still fails. So I'm sort of on the school of thought where, no, it's still pretty far away to actually reach, you know, high level cognition that humans have. And so that sort of having internal coherent model right now, even the best one is still based on CNN and transformer models where no one understands. It's really simple. It's impossible. You don't have memory, you don't have external storage. It doesn't, you know, it cannot learn from the past, as in once you train, it's done. You cannot, you know, gather or collect new knowledge on top of the previous one. And the entire thing, like, I think I like your example of previously we try to copy the process in the brain, but right, even the backprop, the main algorithm used to train the network, is not like our human students don't do backprop. You can't do backprop. So that alone, just, you know, it's already different. And right now we don't really care how humans work. Neuroscience still try to map things back and forth, but a lot of, I think, majority of the time, researchers in this field don't really try to match it back. We just come up with impossible neuron architecture that humans' brain can't replicate. But yeah, I don't know the you know, the view of the entire communities. This is only my own.
Thank you. I think maybe some students would like to ask questions. Anybody on the Zoom? The Junwoo or Manasnan, or okay. You have questions?
Now, like after every lecture, like this is not really question, but something I want to say. Like actually now, like the deep fake technology getting even higher, even better and better. It's sometimes it's easy to disguise some kind of like so-called clues or evidence. Also, that will make things like even much more complex than before.
Thank you. Other question? Let me ask one question. It appears that you could do almost anything with the current power of computing now. What would be the most difficult task that your people in your area is trying to achieve? You know, some kind of most difficult problem that you know, using the image technologies you try to solve and would not be able to do it now, but you hope that you could do it in the future.
Okay, thank you. So maybe the first question was maybe some thoughts on deepfake, right, from Zen, and then the other one is from, you know, the computation. So let me answer the second question first. So in vision, vision is also part of AI, and AI has this, you know, the holy grail of AGI, you know, match exactly human intelligence, and for that, it's still pretty far away, I think. Image captioning, the problem in vision where you have input image and want to describe the image, I think that one is already hard. You know, people can't really fully solve that one yet. And also in general, I think people try to reduce the gap of learning efficiency of humans and AI. Right now, as I said in the presentation, the way we train an AI model is to throw it a lot of tons of data to teach it something. But humans don't really require that kind of large amount of data all the time. Even though, one could argue that we actually have video input from birth to now, which is a lot too. And so, but, how do we consolidate those kind of things? How do we given a new task, or I can teach someone a board game with just a text rule with just a few words, and then you get it. You get how to play it, but then that's not how we train AI currently. So that's sort of the one main problem.
What about consciousness? Would you be able to train AI to have its own consciousness?
Yeah, I don't think I have any authority to comment on that neuroscience perspective, but even consciousness, I don't know what,
They know just robot, you are you.
Yeah. One way I would say we might not have conscious, we believe we do, but we might not. We just some running computers too. So it's very philosophical. I don't know. I don't think I have an authority to answer this, but yeah.
Yeah, I kind of think in agreement. It's not that we're gonna have get to the point where the computer is gonna get so complicated that it can arrive at consciousness. I think what's most likely going to happen is it's going to turn out that our own consciousness is no magic. It's just a bunch of immersion process. Because computer right now can feel pain, right? So in Buddhism we have this khanha, right? So we have vedana, and I think sankhan is a little bit difficult right now in computational science, but we can certainly simulate pain, vedana.
Exactly.
So I think
we can simulate all the pains and replicate completely the behavior of a human being, but would that give it consciousness? It's unclear. Also, there are also interesting different schools of thoughts whether AI will beat humans or will it ever get smarter than humans. And I believe once it reaches there, right now we don't really understand how this even neural networks work internally, and at some point I think I feel like we will never understand how it works. It's just like when you talk to a really, really smart person, and when you ask it, how do you solve this problem? You would not understand it because they're sort of smarter than you. So you can't really understand something that's smarter than you by definition of being smarter. And once AI is smarter than you, I don't think so. There are a lot of people who work on try to understand the inner principle of all this neural network. But I feel like eventually we will not understand how this works. We will not understand the thinking process of AI. But this is just one, school of thoughts in the entire field. So maybe I'll get back to Zen Wu's question about, or maybe could you repeat the questions a little bit? I missed. Or did you ask? I'm not sure whether that was a comment or a question.
Jen Wu, you are here, right? I think he's.
Okay.
It's
Anyway.
okay. It's okay.
Okay.
Well, I think the time is up, and we would like to really thank Dr. Supasorn for this eye-opening talk. I think it's really impressive, and I really look forward that you being at the VISTEC, you can help Thailand being a kind of hub for AI, at least in the graphic vision or whatever. So thank you very much for your kind talk today, and we look forward to get your agreement to come later on, perhaps next year sometime, and we look forward to bring the student to see your lab.
Sure.
The COVID situation has improved.
Yes. Yep. Thank you so much, Kap. Thanks for having me. It's my pleasure.
Thank you.
ขอบพระคุณครับอาจารย์ครับ
ขอบคุณมากครับ Thank you. So the meeting is adjourned.